Bismillah ar-Rahman ar-Rahim. Welcome back to our course, Deep Learning for Computer Vision. Today we'll continue our work on machine learning part. Specifically, we'll tackle today the issue of the performance evaluation of a machine learning system or network. Now, suppose that you have designed a network, you have tested the network by training, validation, and testing, and you get good results. Now you want to either to compare with other systems, other neural networks, or other machine learning algorithms, or you may be able or you want to specifically define some parameters, some metrics for this developed machine learning algorithm with your own hyperparameters in this system. So how we can measure the system performance, what are the metrics that can be used in this situation. This is the main intention behind this lecture. So let's jump to our lecture slides and proceed further. So the performance of or the performance evaluation metrics in machine learning will be our main topic in this lecture. The decision guidelines are as here. We have to take a tour on performance evaluation metrics regarding the regression, the classification, and at the end of the lecture, we'll have a MATLAB mathematical tour regarding the classification, what we call it, the classifier learner, as will be explained later by the end of this lecture. In general, when we design a machine learning model, we need to evaluate its performance, and we want to understand, is it working very well? Is it okay? Or we need to improve it more and more. So in this case, what are the measures that can be used in such a situation? What are the proper metrics that can be taken to evaluate the level of the performance of a machine learning model? These metrics are usually known as performance metrics or evaluation metrics. These metrics help us to understand how well our model is performing, is doing well or not, and this will help us in improving the model's performance by going back to the design or the analysis and describe or tune our hyperparameters that were taken, or maybe the loss function that was used during the machine learning, let's say, design or building of the model. So mainly we need to tune our model to get better performance by tuning the hyperparameters and by, let's say, maybe taking actions regarding the loss functions and maybe other issues also. In general, we can divide the metrics in two major types. Here we may have the first type as for classification. In case of the classification, as you see here, we have a list of evaluation metrics. The main one is the confusion matrix, that where we can find out the accuracy, the precision, the F1 score, the AU, UC, ROC metric or graph, log loss, Gini coefficient, etc. The list is long, and usually we use mainly the accuracy, precision, recall, F1 score, and the curve under the ROC, as will be explained later. For the regression, we have a few measures. Of course, we may find others or other measures. Mainly, we have the mean absolute error, the mean square error, the root mean square error, the root mean square error, log error, and the R squared and R square adjusted errors. Mainly, we may use usually the first three types, or the first three metric measurements, and this will be useful in deciding either to go further or to stop working with this, or by changing or modifying the parameters in our algorithm in machine learning. Let's start with this assumption. Having the target, the output, and the y dash or hat is the predicted output. Now, to define the mean square error, we want to find the error in this case, as you see here, as the difference between the squared error, the average value of the squared error of all between the target outputs and the predicted outputs. And this gives us about information about the mean square error between the desired outputs and the actual outputs that we are performing or doing in our model. Now we can take the root of this equation by taking the root MSE. So we just take the root of this value, which is the MSE value. We also can take only the mean absolute error. This can be done, as you see here, we have just replaced the MSE value. So instead of taking the squaring, we replaced this by a absolute error or difference. And this is done usually to reduce the calculations and the computational cost of the measuring metric. And in this case, it will be sort of speeding up our processing if it is required to apply or do this every time during the iterations. And it actually, in fact, it can be very useful, which is sometimes very comparable with the when we take MAE instead of MSE. It gives you a good indication about the performance of the system. But we still need to know what is the R squared and what is the adjusted R squared. These metrics, you can see it on and search for it on the net, and you'll find out of tutorials and with examples on these measures. For the classification metrics, we can find a list of metrics as we have just at the beginning of this lecture. We have just mentioned that. Now, the main idea here is are based mainly on the confusion matrix. Then we may define the accuracy, the precision, the recall, F1 score, the specificity, area under ROC curve, and maybe more. There is still maybe 2 or 3 other measures that can be used in case of classification or maybe in advanced classification approaches. However, these will be enough and more than enough to understand and get good information about the evaluation of your machine learning algorithm or model, and you can, you can get your decision properly without any harmful actions. Now the confusion matrix. What is the confusion matrix? In general, it's a matrix. It's a matrix in general that summarizes the performance of the machine learning model on a set of test data. So you apply a set of test data. We here mean by test data that it could be, you can find the confusion matrix for the training data set, for the validation data set, and for the testing data set. No matter the input data set, you can, once you have a test data applied to the machine learning model, you can build the confusion matrix. It displays the number of accurate and inaccurate instances based on the model's predictions. So where we have achieved, let's say, correct output, or where we have a fail in finding the correct output, whether this is for positive or for negative actions or maybe situations. Now, in binary classification, we are using categorical. This means that we have either class 1 or class 2, either 0 or 1, maybe either 1 or -1. So in this situation, we can define 4 definitions or maybe terms. The first one is the true positive, TP, and the true negative, the TN, the false positive, and the false negative. These 4 terms are useful and very important in proceeding further in understanding how the confusion matrix is designed or is constructed. So let's look at this matrix. As see here, we have on the y-axis, okay, we have the actual values received from your model, and this is the sorry, the actual values that are correct, that are designed in before, so are given as a supervised learning method, and here the predicted that are obtained by your system. You can reverse the x and y axis with no change in results. Now, suppose that you have here, let's simplify our task by saying that the positive means we have a dog. Let's take another pen. Okay, so let this be a dog, and it's not a dog, maybe a cat. Just two categories. Okay, here we have cat, maybe a dog, the same order, and a cat. Okay, now when you achieve true positive, if you get at the up to your system a dog, and in actually it is also a dog, so you know that this is a dog, and you categorized or you classified it as a dog, so this is a true positive, a true positive. Now let's go to the negative part. Here we have a cat, okay, and suppose that you categorized or classified the output as a cat, and it is also a cat, but it's not a dog. Maybe we use the true and false, maybe better for presentation. So let's go and get rid of these things now. Okay, let's pick another pen. Suppose that in your system, here you have positive, this means that it's a dog. And here we have not a dog. Maybe this is easier. Here we have a dog, and here we have not a dog. Okay, so in the first time, true positive means that you classify the input dog, and it is actually a dog. Let's go to this space, to this element. Now, you have classified the input as not a dog. It's not a dog, maybe something else, but actually it's a dog as given by the actual or the true label. So you have a positive, you have a dog, and you classify it as not a dog. So this is a false, but a false in negative, because you get not a dog. If you go now, let's remove all these here, and this one, okay. Okay. Now, let's go to this second option. You get not a dog, and actually at this location, and it was really in the true labels or in the actual labels as not a dog. So we classified the input as not a dog, and it is actually not a dog. So it's a true negative. So we have true positive, we have a true negative, we have false negative. So what about false positive? This is the case. Now, if you have classified the input as a dog at the time that it was not a dog, so it's a negative input, so it's not a dog, and you classified it as a dog. So this is actually is a false positive. Positive, why? Because you give it the class of a dog at the time that it's not a dog. Why it's a false negative, for example, at this location? Because you classified it as not a dog at the time that it was a dog. It's opposite to the, here we have opposite operation or decision. So and this is the situation where we can, in this matrix, we can summarize all the information about our decisions in respect to the actual or the true labels or the actual classes applied or stored in our system. So mainly, true positive means the prediction of positive, a dog, for example, and the actual is also a dog or positive. Here for the true negative, the prediction is negative, not a dog, and the actual is also not a dog. Okay. Now, when we talk about the false negative, the prediction is negative, but the actual is positive. So you classify this sample as being not a dog, but at the time it was actually a dog. In the last box here, the prediction is positive, so you classified it as, for example, a dog. At the time, it was not a dog. So you see here positive and negative, negative and positive. So you can categorize all these things consequently or accordingly. Let's see this case. Here we have lion, fish, monkey, elephant. These are the actual, and these are the predicted on the x-axis. So we have elephant here. So if we are talking about the elephant and the monkey and the fish and the lion, these are the predicted values, and here the same are the inputs or the actual or the true label, the true or the true labeled data coming from the supervised learning method. So what we can do now? How we can understand these things? Let's wait until we go back to the first step. Again. Okay, name back, sorry. So as you see here, we have at this location, we have classified the elephant. Oh, sorry. We have classified the elephant as true positive because it's an elephant and the class is also an elephant. For other classes, you see that we have classified the elephant as a monkey for first time, as a fish and a lion. So these are the false negative for this case. Now we have an elephant at the input and we classified it as an elephant true positive. We classified it as a monkey. This is false positive. As a fish, false positive. As a lion, false positive because it's an elephant, and we classified it as something else. So it's a positive, but the classification was false. Now for true negative, we can continue for these parts here and define the true negative for all these components. For example, we have a monkey. We have a monkey for now. We are working with the elephant. This matrix is defined for the elephant and not for all other components. Let's go maybe next step and see this. Now we go to the monkey. Step 2. Okay. Now for the monkey, at this location, we have the true positive classification samples because we have here the monkey. So this is monkey and monkey, so it's a true positive. Now, other parts, for example here, if we classify the monkey as a lion or as a fish, this is a false positive. Also, if we classify the monkey as an elephant, it's a false positive. So we have here the true positive, and the other part here and here are the false positive. We'll continue for other steps. Of course, we can let this animation go further and continue for other. As you see here, we only go to the fish, then we go to the lion, and these are similar for all. In case of we have not only 2 classes, maybe four classes or more, to specifically define where is the true positive, where is the true negative, where is the false positive, where is the false negative, and this will be very helpful in understanding all these things. Let's have an example on on CM. In an image recognition task, we have inputs being animals, including dogs. Okay, so we have a dog, not a dog, dog, not a dog. The experiment has been recorded as one in this table, and we know what we want now to construct the confusion matrix. If you look at this table, you can see that this is the actual and this is the predicted. The actual was a dog and the predicted was also a dog, so it's a true positive. The actual was a dog, but the predicted was, so our system, our machine learning model uh, predicted or recognized that is, because we have a recognition task, that it's not a dog. And this, in this case, we have a false positive, false negative. Next, we have a dog at the input, the output dog. Okay, it's okay. Now it's have not a dog. It's have not a dog. Let's remove all these things to show it easily. Okay. So suppose that you have the actual as not a dog, and you classified it or categorized it as not a dog. This is a true negative. Now let's have another question. For example, yeah, in this case we have a dog, and we have our classification not a dog, so it's a false negative. The negative is false. Now we need to construct the confusion matrix. As you see here, dog, not dog, positive and negative. And this is the true positive. How many true positives we have here in this table? We just need to calculate. This is true positive, true positive, true positive, true positive. So we have, and this one also. So we have 5 true positives. We have, as you see here, we have uh, 5 true positives. If we want to find the false positive, we just need to measure the false positive. As you see here, we have just one false positive. Let's remove all this here. Yeah. Next, if we want to find the false negatives, Fn, false negative, we have one only, again. And if we want to find, for example, the true negative we have here, we see here we have 1 true negative, 2, 3 true negatives, and we get 3 true negatives. So by this way, we constructed the confusion matrix for further processing to find the actual and to find the evaluation parameter metrics for machine learning evaluation. So we have here 5, here 3, here 1, and here 1. One of the main, let's say, measures or metrics used in machine learning models is the accuracy metric. So the accuracy in general is a metric that measures how well a model can predict outcomes on new data. What does that mean? So we measure the correctness or the accuracy of the model in predicting the incoming, let's say, samples or points in the data set to be classified correctly. Now, accuracy, in fact, for classification issues, it represents the most intuitive performance measure in machine learning when we talk about classification. But when we talk about other tasks like, let's say, segmentation, let's say, object detection, and other tasks, it may not be working very well. However, for the classification issue, the accuracy is one of the most important and intuitive performance measures that can be used in quantifying the, let's say, the performance of the machine learning model. It can be calculated as accuracy is equal to TP plus TN over TP plus TN plus FN, FP plus FN. How we can understand this equation? Simply, you see that here in the numerator, we have true positive and true negative. So we have correct actions divided by all actions in the input or in training or maybe testing the system. So if you apply, let's say 100 samples, and you could classify the true positive and true negative, let's say 85 times correct. Now you may divide this by 100, the overall number of input samples, because here we have true positive plus true negative plus false positive plus false negative, all combined together give you the size of the input data set or the input data samples, let's say. simply. So this is a very important parameter and can be used specifically in classification issues in evaluating the performance of the machine learning system. Now, the precision and the recall, they are very close to each other, and mainly the precision is a machine learning performance metric that basically attempts to answer the question. Let's simply say that this way. What proportion of positive identifications was actually correct? What proportion of positive identifications was actually correct? So it will be true positive divided by true positive plus false positive. So you have 100 samples. You could find or correctly classify the true positives, and you missed, for example, 90, and you missed only 10 samples. So you have 10 false positives. In this way, you get 90 over 100. So this is the true positive plus false positive. How many of the samples that are actually correctly identified? So this is the case of when using the precision. It gives you, from its definition, precision, the precise, the precise, let's say, preciseness of the machine learning model in classifying the input new samples to the system. Now, the recall is a machine learning performance metric again that basically attempts to answer another question. What is the question in this case? The question says, what proportion of actual positives was identified correctly? So we take here the true positive divided by true positive plus false negative. False negative. Here, false positive, we replaced it by false negatives. So the answer to this question is this way, is called the recall. So what proportion of actual positives was identified correctly? So true positive actually divided by true positive plus false negative. This will give you the recall measure or metric for your machine learning model. Now let's go to the F1 score. The F1 score actually is an evaluation metric for classification issues. It represents what we call it the harmonic mean of precision and recall. So it's a sort of averaging of the value obtained from the precision and recall. Actually, when you deal with machine learning models, sometimes the data sets that will be available for different classes, usually they are not in real life, they are not balanced. And this will cause to give you a fake accuracy maybe, or fake, let's say, resolution on your ability of your system or your machine learning model to, let's say, classify the inputs in case of applying new inputs to your machine learning model. So F1 score is a good measure to override the problem with the overfitting or the fitting issues that we'll talk about it later on by applying this metric. As you see here, we have F1 score measured as the harmonic mean of the precision and recall. And in this case, you just need to multiply 2 by precision multiplied by the recall divided by the sum of the precision and the recall. In general, the value of F1 will be between 0 and 1. Yes. And the higher the value of F1, the better is the accuracy of the model. Of course, you see here when you have low precision, this number will lead to reduce the F1 score, and because it is reciprocal of the precision. Now, when you get low recall, this will also reduce the value of F1, and both are interacting to define the F1 value. This is very important in machine learning models, and it is usually a good measure of the system accuracy performance. Let's have an example here. Given an ML classification task, machine learning for classification task, that resulted in this confusion matrix. Now you are asked to find the accuracy, precision, recall, and the F1 score. Now we'll start with the accuracy. This is the equation for the accuracy. Here we have, as you see here, we have the equation, true positive plus true negative, all divided by all over the number of samples applied. So we have here for true negative 55, for the true, for true negative 55, and for true positive we have 30. So we get this number divided by over all the numbers in the matrix. This will give us something like 0.85 or 85% accuracy. This accuracy is considered as in general a high value. Usually the accuracy will be in modern machine learning and deep learning models maybe approaching 99 and 95, 94, 96. This is the range for perfect models. However, 85% is not a bad result. Now let's measure the precision. So as you see here, the precision as well seen, it will be true positive, which is 30, here 30, divided by the true positive and false positive, which is 30 plus 5, 30 plus 5. So you can see that this matrix has been inverted when compared to the one discussed in the previous slides. No problem with that. The order is not very big deal. However, you have to just manipulate where to put these values exactly. So the precision is about 85, again, 85%. It's between 0 and 1. This is also a good output. For the recall, if you repeat, you can find it's 75. So you see here the recall has little bit lower performance as a metric or a measure. It gives you lower value. This will lead to reduce the value of F1 score, and this gives you, even we have an accuracy of 85%, we have the F1 score little bit below 80%. And this indicates that there's some maybe improvement can be done, procedures can be done for improving the performance of the system in general. Now, the last, maybe not least, but the last one for the machine learning it's usually used is the area under the ROC curve. Here, this curve is used to visualize the performance of the classification model on charts. So you can use a chart to visualize the performance of the classification model in your visualized in two-dimensional curve. Now, the receiver operating characteristic curve, this is the ROC, receiver operating characteristic curve, represents a graph that shows the performance of a classification model at different threshold levels. So when you take different threshold levels, when you apply different samples at different time sequentially, then you get different plots for having what we call it the ratio between the true positive rate and the false positive rate. So in general, the true positive rate can be found as the true positive divided by true positive plus false negative. So we have true positive divided by true positive plus the false negative, while the false positive rate is the false positive divided by the same amount, which is the false positive plus false negative. So what is the portion of the input having the for positive and negative samples are correctly defined as true positive for the true positive rate, while for the false positive rate we define this as what are the falses done with the positive samples when applied to the machine learning model. Sometimes we call this equation as specificity, and this equation is called also, which is the true positive rate, as the recall or the sensitivity. Again, it's repeats the idea of the recall, and sometimes it is called also sensitivity. This is not our now story. The main idea is to find the curve in 2 dimensions that represents the modification or the changing when changing these parameters, how it will affect this curve. Now, as you see here, we have the false positive rate, and on y-axis we have the true positive rate, and we sketch for different threshold values until we reach the max value here, and it starts from 0, 0 up to 1, 1. And the area under curve now can be, it calculates the area under this curve. This is the area below the ROC curve. This is one of the important metrics that can be used in defining the performance of the machine learning model in general without going to numbers, just from the curve directly. Let's have this demo. So as you see here, we have, let's zoom it maybe a little bit. Okay. Yes. No, a little bit. It's okay, I think. So if you look here at the if you look at here, everything above the cutoff is a positive prediction label. So we have here positive. This is your threshold, and this will give you these are the actual labels. Above the threshold will be 1, and below the threshold will be -1, and this is the actually the what we call it, the confusion matrix. And by changing the threshold, we are changing the false positive rate and the true positive rate and measuring these values. With time, we can now okay, I'm trying to again to zoom it a little bit. As here, the curve is moving, and it represents a two-dimensional curve. The area under this curve is about 75 or 76% of the total curve, which is equal to 100% of 1. And this gives us information about the performance of the system. It looks like that the system is a little bit needs improvement, and more or less it is considered as maybe as a good system, maybe good for some applications. If we go to another example here, see here we are taking the values and measuring the ROC curve and finding this is the perfect case when all values are correctly let's say classified, and with no errors because the false positive rate, the false negative, the false positive rate is the true positive rate is always 1, and the false positive rate is always 0. And this gives us a curve with an area under graph under this its graph is 100%. And we think that in this case we have a perfect system, and this is maybe an ideal case, or can't be usually achieved in real applications. However, this is a measure or a comparison between two types of systems having different ROC, let's say, area under graph. We'll go now to see some MATLAB examples. We have three main apps in MATLAB: classification learner, we have regression learner, and we have also reinforcement learner. We can just click one of these and go and see what are the abilities to use these learners and design tools to find different machine learning tasks. Let's go and jump to MATLAB and see what will be going there. So these are mainly we have for our tasks, we selected the classification learner, the regression learner, and the reinforcement learner. If you click on these links, you will open a website on mathbox.com that will help in defining or help you in understanding and comprehending the links here. Let's start with the second one, skill verification. This will be about the classification learner. We can start here and see description, details about all these things. We can start with the examples. Also, we can understand all these things here. If we click on the train classification models in classification learner, let's pick the first one, this one. Okay. Sorry. Okay, let's pick the first one, classification train classification models in classification learner and go to this link. If you go further, click on the link, you will be forwarded to the train classification model in classification learner app. You can read all this data. You can see what we can do. However, I'll help in just understanding general situations. You can do automated classifier training. You can do manual. However, we can go now further and pick below here. We can take now select data for classification or open saved session. In fact, the main problem in machine learning is that in providing a proper data set for training. This is the main issue. If you have the data set for your training system, you can train it and get change the system itself and changing the learning model. You change the hyperparameters, tune it, and you may achieve high performance. But the main issue is to have a good data set for in this situation. Now, to do that, in MATLAB, it's very hopefully, fortunately, we have a list of examples on data sets for classification. Here, the same thing for the regression, but I have talked this part only. Here, you can upload the Fisher iris, for example, sort of three species of iris, three types or three classes of iris. You can read this table. Usually, the input dataset is designed either in matrix form or in comma separated variables, which is CSV, or it could be in vectors. And here, the number of, as you see here, the number of predictors is 4, the number of observations is 180, number of classes is 3. The response is to, we want to define what is the type of this iris respect to the inputs applied in the dataset. So now let's go and open MATLAB. It will take a while, and copy this file as here, Control C, copy. Can just evaluate directly, but we can just copy this. Okay. I hope that it's already opened. Let's finish with this lecture now. Okay. Let's close all these windows. Now, I try to open MATLAB again. I think I have some delay. So we have already, if you just to wait for a while, we have already other also data sets. You can also find other data sets may be available on the net. On the we'll see a list of links to data sets like GitHub, like the PyTorch and the Coco data sets. You can find a lot of things here there. Now we may talk about other types of. I'm just waiting for MATLAB to open. So we can find, you can also build your own data set by applying it, by making testing labs maybe, or getting from a friend from some companies. So you can do this on your own also. However, in MATLAB here we have, we need to wait a little bit. I think it's just loading. So this is our MATLAB. It's opening now. We have already copied, as you see, we have copied this the first dataset table, this one, yes, and we try to upload it to the MATLAB. It's working. So let's print now. Before printing all these things, we need to go to the apps. Here we have the apps. If you see the apps here, and to go to this scroll bar and select one of the machine learning and deep learning apps. Here we have a list of apps. However, we can select firstly the classification learner. We click on the classification learner, and meanwhile, let's copy and paste our matrix to MATLAB. So after performing this function, you see that we have here a table. If you double click on it, you will see the details in this table. So here we have here, as you see here, five columns, and maybe a list of inputs, 150 inputs. Now every column represents a specific feature, which is, for example, here sepal length, sepal width, petal length, and petal width. So it measures the size of the iris flower and gives you, according to these parameters, that this is the type is, for example, setosa, or a sort of if you look at what is setosa, or let's increase this one. This is versicolor, and we have also another class. Third class, it is Virginica, etc. Now let's see what is setosa, for example. So if you go to images, you can see, for example, this is the setosa that we are talking about. We are here also Veronica. I think this is true, right? No, not Veronica. I think it's something very close in spelling. Virginica. Okay, I'll go back. Virginica. It's another type of flowers, very close in shape, but it has other measures or features. So in our table here, we have 4 different measurements or features of this input. And according to these parameters, we can define that this is the species or the type of the flower is setosa, or maybe virginica, etc. for the other versicolor, etc. So now we need to, having this matrix here, we'll go to the classification learner. It's already opened. Here we need now to start a new session. So let's click on plus to start a new session. So now this is the window opened as a new session. Let's zoom it on. Now here we can select the input, which is the table in our case, here the table. And then we want to find the response from the table. So what is the output? The desired output is the species type. And here we have we call it the predictors. That are the input features that are applied to the machine learning system. It's sepal length, width, petal length, and width. So now we start the session. However, you can go to the right-hand side here. We have the type of validation. You can use cross-validation, hold-out validation, resubstitution validation. What is the difference between all these types? Actually, you can read it in the MATLAB, in this file. If you go to this file, let's go and see. If you, okay, it's not working very quickly. Now, the cross-validation, you are dividing you can say that it divides the input data set into folds or into parts, and it operates on these parts, then combines the average value for all parts together. For the hold-out validation, another type of validation, the same thing for the substitution. Now it will take a lot of time to talk about it. Usually the default for this cross validation Let's keep it as is. It will be 5. And here we can take a part of the data set applied to leave it for the testing. Here we can select how many persons that we want to keep for the data set. This means that this part will not be applied to the machine learning during training. It will be only applied after accomplishing the your final result in and building your unit or your model. In this case, you can apply finally. This is the input data that was not tested before, and you can keep it as 10%. Let's start this session now and see what we can do with it. So you can see now, this is the summary of our model. In this case, we by default, MATLAB starts its own model, the first model, which is the tree or the fine tree, decision tree, and it talks about this type of model of machine learning model. Here we have also the data scatter plot. These are the samples that are available in our data set. You can here on the right hand side, the right down bottom corner, Setosa, can remove Setosa, keep only vesicular and virginica. You can also keep only one type. Anyway, we have three different three different responses or three different outputs. So we'll keep it as is. Now let's start our training. Now, how we can use machine learning training? If you go here, you can see this one here. You can now find or see what are the types of, let's say, machine learning that is proposed by MATLAB. You'll find a long list of applications. You can apply all quick to train. You can use all to train, or quick that will be training will be very quickly. Some some machine learning techniques are very quickly. Others are a little bit slower. You can select all in general, or you can select all just the linear type of these machine learning algorithms. Here we have decision trees. We have discriminant analysis. We have logistic regression classifiers. We have naive-based classifier, support vector machine, and nearest neighbor classifier, kernel approximation classes, and simple classifier, etc. All these neural network classifiers, you can see here we have different neural networks. Let's start with what we discussed in the previous lecture. Let's take, for example, the support vector machine and take the quadratic one, not the linear, because here we have a two-dimension curve having second order. So we pick this model here, model one, model two. This is the information about our model. Here we have some details, the kernel scale mode. All these parameters you can learn about it from clicking this link and taking some info about it. Now we selected this, let's say, model, and we now try to train it. We go here to make training. Of course, sometimes you may use, if you look at this corner, here we have train and use parallel. The train is, as usual, we train the input data to get the response or the output decisions. And now for the parallel here, use parallel. Usually it is set on all computers. Sometimes we may need to use what we call GPUs instead of CPUs, which is the graphical processing units. And some computers are provided with these units and can speed up condensely can improve the speed of the training issue. However, in our case, we selected a small data set just for demo purposes, and let's start training. Here we can train all data sets, or we can train selected. In this case, we selected just the quadratic SVM, and the training is going on now, and we'll wait for a few time. You see here that it's opening, working now. So you see here the train is moving. Here the train is moving as here. It is running and the train is running. As you see here, we have a result of 95.6 for accuracy. And we can, as you see here, we can already can sketch or it is sketched already the confusion matrix for the three types of, this is the true table of the Setosa, versicolor, and virginica, and here we have the actual or the predicted classes by our system. As you see here we have 45 out of 150 Setosa. It is true positive. 141 for versicolor and 43 for virginica. And we have missed very few samples. It's four that were virginica and they were classified as versicolor. And we have two samples here that were classified as versicolor and they are actually virginica. So the system looks fine. The performance is very high. Now what we can do also here, we can go to this part of the scroll bar and click it. We can now sketch many things like, for example, if you look at this, it will be the ROC curve, confusion matrix, parallel coordinates, ROC, etc. for the data for the validation test and for the validation results and for the test results. Let's sample, say, for example, let's see the ROC curve for the validation data. So as you see here, it's very clear that, for example, for Setosa, here we have selected here, for example, Setosa. This is the ROC curve. For versicolor, we have to pick for versicolor, let's see. Let's take for the other one. And now let's take for all together and see what will be the output. Let's erase or clean here. So you see now from the curve that almost all curves are with 100%, this little bit less than 100%, with Setosa being the best one, and some mismatch was happening in versicolor and virginica. Now, what can we do also? We can find also other actions here. We can export the figures to some file, let's say for export for an external file and keep it there. This is the curve, for example. You can change your inputs to get the proper curve for your application. Okay, and you can save it as either .fig for MATLAB or .bmp, JPEG, etc. You can export the model. For example, export this model with inputs and with all details, or you can just export compact model with only its own parameters without extra details. If you look at here, we can export the current model, for example, for train model, let's say 1_1. So, okay. If you click OK, if you go to MATLAB workspace, you'll find this model here already stored. If you click on it, you can go and see all details about it. You can see here all the information required for the model. You also can, if you go back, record variables here, forced variables. If you go again, this is the SVM results. You can click all these and you see what was done and what are the output parameters, etc. All these things can be found in this structured variable. If you go back to here, to the classification learner, you can also export not the model, you can generate the function of the model that you have implemented. We have already generated it here as an untitled file. As you see here, it's a function that makes training according to the training data that you will apply for this time or for other times. Here's some information about this is comment data or text. You can take now the actions that were done in the SVM model, and you can now change your input by replacing their training data by your Fisher table or by maybe other tables that are designed by either by you or by others and prepared for this purpose. I think we can also now we can continue by selecting specific, let's say, different types of, roughly speaking, these, and the system will, MATLAB system will train it for you. You can select all, as I told you before, and things are moving now, and the performance is it will appear on time. Just now to save time, we need to stop. And I think for today, thank you for listening. I'm sorry for being very because we have a long lecture today, but actually it's a very important lecture, and I hope it was very helpful and useful for you. And see you, inshallah, soon.